Sweet. Hey, all y'all, how we doing today? Good to see you on a cold, rainy, disgusting Tuesday. February already, holy crow. Yeah, Christine, I'm a Bernie libertarian. Have been a long time. Love Bernie. Dev. Ideal weather for what? For coding, maybe. Oh, thanks, Malik. That is, I assume you're talking about the SG. That's the 61, it's a 61 standard reissue. Just came out last year, I think. Sweet, as a sweet machine, man. Nah, I don't play for people so much. I'm not that good, but I love to play. I play constantly. I was a music major before I got into engineering and computer science. I was a music major at Indiana State. I was a freshman when Larry Bird was a senior. If you remember Larry Bird from the Celtics and the Pacers later on. Yeah, at some point I was walking in. It was my first year. I was walking into a music theory class and kind of realized that I wasn't that good. Like I had a full scholarship for music. Was walking into class of some theory class. Like, you know what, Donham, you're going to be teaching junior high school band the rest of your life, and I just couldn't face it. So I turned around, I walked out, and I never went back. I dropped out, and then a while later, I was fortunate to get into an engineering program and got a double E degree. But yeah, I started out with music. I would have done computer science, but there were no computer science degrees back then. It was all either engineering or math. Yeah, Bertie, he does. You know, it's the same with oh, what's his name? Shoot, I campaigned for him. Why can't I think of his name? Dukakis, like in town in Boston. Dukakis is all over Boston. Like if you're on the T, especially the Red Line, you're bound to run into Dukakis just walking around. He likes to pick up trash. So they're just regular guys, just like us, right? Except Bernie. Okay. Hey, so let's talk. We were going to talk about loops today and stuff, but we didn't get to it in A1. So just a lot of stuff to talk about, I guess. Data types for sure we're going to talk about. And I'll stop at the same place that we did in A1. So we might stop a few minutes earlier. You know, it's always B1 is always a little faster because I've figured my shit out by that point, usually. All right, so just a quick reminder, PS0 is due, when's it due? Friday, I think? And also just a reminder that everything you need is pretty much on Piazza. Go over to Piazza and look in the resources tab. So you're gonna find our recorded lectures, lecture notes. Here's today's lecture note if you wanna follow along on the slides. There's your homework. We'll post solutions up there at some point, possibly, probably, should. And in terms of submitting, basically that assignment, you just fill in the PDF and then it gets submitted on Gradescope, and then we'll grade it from there. So it was just your convenient reminder. All right, let's talk types. So this is kind of falling out of, you know, actually PS0, those printf statements, those formatted print statements, like you have to specify what you're printing, right? %I, %D, %X, %G, you know, all those things. All those percent things in that printf statement, they're really just, I mean, they're called conversion specifiers. It's telling C what the thing is that you want to print. And the reason it needs to know is that things are stored in different sizes of memory depending on what they are. And it's really picky. So an int, for example, an int might be 2 bytes or 4 bytes. A float is going to be bigger than that. A character, actually, that's the only thing that we're guaranteed. A character is always 1 byte. 1 byte is 8 bits, right? So that's the only thing that's guaranteed in C, is that a character is 1 byte. Everything else has different sizes depending on what it is. So an int is usually smaller than a float, but by how much? Well, here's our challenge. The answer to the question, the answer to most questions is in computer science is it depends. Like if we say like how big is that integer in memory? How much space, memory storage does that int take? Literally the answer is it depends. It depends on what hardware you're running on, what operating system you're running on that hardware. Um, I guess really those two things, but they're all different. So an integer on a Mac might be 4 bytes. On a Linux machine, like an old Linux machine, might be 2 bytes. IBM mainframe might be 6 bytes. Like you just never know how big it's going to be. Like in most languages, we don't care because the language itself takes care of it. Like in C++, if I want to create a new object in C++, I just say new. There's a keyword called new, and it just does it for me. It creates the object, figures out how big it is, stuffs it into memory, keeps track of it, does all those things for me. Let me just make sure I'm recording. I think I am. I am, sweet. In C, nothing is done for us. We literally have to do everything on our own. So all that memory stuff, reading things out of memory, putting things into memory, like we have to manually manage that. And to do that, like we need to know how big things are. So there's a couple of ways to approach this because they're going to be different everywhere. And I guess the other challenge really is like I'm writing code on a Mac. I want to write code that will run on a IBM mainframe, right? C's kind of universal. The C code itself should look the same. It's the executable file that's going to be different. So that executable is going to be very different on a mainframe than it is on a Mac. So I need to be able to like target different environments that have this problem. Like they store their stuff in different sizes. I want to be able to write portable code that works on all those platforms, but like I don't know ahead of time what it's going to run on. So how do we do that? So there's a couple of approaches. One is there's a header file. You've already run into header files with standard IO, stdio.h. That's a header file that defines functions like printf and so on. Well, there's a header file called limits. This one, limits.h. Let's just go open it up and we'll see. Where's VS Code? Jonas asks, can you manage that through different compilers for the different OSs? That's actually how it ends up working. So you'll have a compiler that runs on an IBM mainframe, for example. To create the executable file, you would compile the program on the mainframe. Or the other approach is some IDEs or some systems, you can specify a target. So I can like, it's the same as like if you're writing a game for an iPhone, you're probably going to write, on a Mac, you can write that code, but you're going to say, hey, this is going to run on an iPhone. Same idea here. I take the C code and say, hey, I'm going to run this on an IBM mainframe, and it does the right things for me. The easiest way is just to compile it where it's going to run. But like maybe it's a fancy library that I've created, and that's that's how I make my money, is selling that library to people. I don't want them to see the source code because that's the secret sauce. So I have to have some way to move programs around, get them running properly on a specific platform. We're going to let's look at a couple of ways. Let's open up limits.h, for example, and you can see the sorts of things it has in it. Oops, wrong one. This one, thank you. So I'm already in the container here. I'm just in VS Code. I'm talking to the container, the Linux container. Where am I? I should be root. I am. Let's go find limits.h. So this is a really handy command for you guys. If you don't know where something is on your system, it's where is. Where is. So where's limits.h live on the file system? And it tells you, oh, it's in user include limits.h. Where is this just super handy. and it's got limitations. So where is, actually, I don't have man pages installed in the Docker container, but let me just pop it open here. Did this earlier. So here's the man page for where is. And you can see that, just check standard directories for what you're looking for. So for example, it'll look in user/include, user/local/include, user bin. Those are all standard places that we put things on a Unix system. Windows has the same notion, right? There's the path in Windows. Basically, where is looks at the path and sees if it can find that file for you. Nothing too fancy. That. So that's where it lives on this box. Let's just take a look and see what's in there. I'm going to use a program called More. More just prints out the contents of a file and stops at the end of the page, so you can page through it. You can search and so on. You can look up the man page for it if you like. Let me clear this. Man, whoops, More. Where was it? User include /include/limits. Here's what's in the file. Return. Oh, thank you. Here's what's in that file. Let's see what we've got. We've got, see all these define statements? Define, it's, how can I describe a define? Define is essentially creating someone's like a macro for you. In fact, you can create macros this way. But the way we're going to use this is this value, like schar max, that's a signed character. Let's go down to integers. Here we go. So integers. It's defining int underscore max as, in this case, 2,147,483,647. That's the maximum value you can store in a signed integer. We'll talk about what signed and unsigned means in a minute. So it's different on different platforms. So that value, that 2 billion value, that's going to be different on another machine, another kind of machine. It might be the same, but it could also be different depending on how the hardware is put together. So we need to know these things. How big is an integer? How big is a long? How big is a float? And so on. They're all down here in limits.h. So what we can do is, what we can do is just use limits.h and figure out how big stuff is. So for example, let's pop back to our slides. I'll copy some code. I should mention this, huh? That signed integer that we saw. If it was an unsigned integer, let's go look at the file again. This guy. Let's see if we can find the unsigned integers. Char mins, so chars are always 8 bits. Shorts, longs. Here it is. That's an unsigned integer. So unsigned integers, what this is telling me is that I can store numbers in a variable, that's that kind, but I have a limit. I can store values from 0 through 4,294,967,295. That's the largest number I can store there. If I want to store 4,294,967,297, I'm out of luck. It won't fit, and I'll have to use some other type, like a long or something. So what does that mean? Like, why is it different? Like, what does that mean, signed versus unsigned? Let's go back to our slide. It basically just means that, so an integer on this particular machine is 32 bits. 2 to the 32nd is that number. I should think it's 96 is that number. So 2 to the 32nd, 32 bits. I can store zeros, all zeros or all ones. The all zeros is the value 0. The all ones is the value 429496725 in 32 bits. If I want negative numbers, I have to have some way of indicating that something's going to be negative. I'm going to use one of the bits to do it. So here's an example down here. Actually, this is using 8 bits. So here's an 8-bit number, 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 8th is 256. So in 8 bits, I can go from 0, 0, 0, 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, yeah. 8 zeros or 8 ones. Those are the range, right? Zeros to all ones. Well, 2 to the 8th is 256. So I can store basically 0 through 255 in that unsigned value. If I want to use one of the bits as a sign, like plus or minus, that uses up one of my bits. And so now I only have 2 to the 7th values that I can store. So basically between minus 128 and positive 128, it's still 255 values, but now I'm using one of the bits as a sign. And so it basically splits that number in half. Half of them are negative, half are positive, and that's all I have, right? So that's the difference between an unsigned and a signed value. And what's happening here is, over here, I said, oh, an unsigned int is that big. If I want it signed, that's going to be half of that. It's down here somewhere. I can't find it off the top. Longs, uns, oh, it's here. It's right above it. That's the unsigned value. If I add a sign to it, now I split that space in half. Let's pop back here. That makes sense? You guys are so weird. So A1 is like, A1, I can barely keep up with the chat. It's just scrolling by like crazy, tons of questions. And you guys are like, it's really weird. I don't know why. I don't know why. All right, so we need to find the size of things. Yeah, maybe that, Bernard, I think that's it. Just more, you're one letter more mature, right? You're B1, not A1. A1 is one more than B. Just vibing. Oh, thanks, Jaru. That's not the question I was looking for. Signed versus unsigned, it's actually this. So this is a signed value. The sign just means it has a plus or minus in front of it. That's the sign. That's a negative value. So that is negative. That one's positive. Down here, I've got basically minus 128 to plus 128. Those are the signs. Cool. This matters because when we're working in C, we almost always need to know the size of something. And again, it's because we have to manage memory manually. There's nothing helping us. It's just us and our little keyboard and whatever snacks we have. That's all we have. There's nothing else helping us with memory management. So we got to do it. And then that problem that we have of, well, how big is an integer? It depends, right? It depends on where is what platform am I running on, basically? Am I on a mainframe, on a Mac, on a Linux machine, Solaris, what is it? We just don't know ahead of time how big it's going to be. So we need to be able to ask the system, hey, system, like how big are your things? So one way to do it is just to ask limits.h. Every platform combination of operating system and hardware has its own limits.h file that defines the sizes for that platform. So we just copy all this, copy that. I know I can't manage without snacks. It's what I live on. Let me create a new file, new file, save it, and let's call it B, B size or something. B for B section. .c. It's gonna be a .c file. Paste the stuff in from the slide. All right, so I'm going to use standard IO in this case. I'm sorry, limits.h. So limits.h is this file down here, this stuff. And it defines uint max. So in fact, it's right here, right? Where do we find it? There it is. So uint max for this system was defined as 4 billion something. Well, let's print that out. So an unsigned int has a maximum size of, this is read from limits.h. And somebody mentioned in A1 that that include statement is essentially like the import statement in Java and other languages. So it's just really just importing that file for us. It knows where to find it because we use these gangster brackets. If you use the gangster brackets like this, it says, hey, this header file, this .h file lives in a standard place. If it's in a non-standard place, we'd have to do something else. We'll see that later. Nice. All right, so let's save that and let's go and run it. Let's clear the console out. What do I call it? B-size? Cool. So let's compile it. GCC -o B-size -o B-size size.c. And by the way, for this lecture, I'm going to compile stuff from the command line just because it's easier. So, I mean, most of you probably are just doing this, right? Build in debug active file. And it says, which one do you want? I want the GCC build. It goes and builds it, et cetera, et cetera. What? Who knows why? I don't know. I probably screwed something up. Just stop it. It's just a lot simpler to do it on the command line. And so that's what I'm going to do. It's essentially the same process. You're still just compiling, right? So I'm going to say GCC, go do it. Oh, that's why I just shoved all that stuff onto the command line. Great. So it's compiled. And then we're going to run it. The output was bsize is the executable. So let's just run bsize. And what we get is an unsigned int has a maximum size of, there it is. That came right from limits.h. Stick a nice little back end on that. In fact, it's changed it. So let me just go and recompile. There we go. So unsigned ints, just read the value from limits.h, print it out. It happens to be an unsigned integer coming out of that. And so we use %u here to tell it's an unsigned int. Cool. Other stuff we can do. There's a size of function, and that's built into the base language. There's no includes or anything like that. Bernard says, do we have to memorize all the % modifiers? No, they're all on page 555 of your CPAM book. It happen to have it open here, which is why I know the number. Or just look them up. Just, look them up online. But Bernard, like, keep in mind that they really do matter, right? So you have to match them up. The type of the thing you're printing has to match the type of the thing that's in the format string. So like here, if I'd done, let's do it. So that I know it should be an unsigned int, but let me change it to just like a decimal, which is an integer, right? Maximum size of -1. Actually, this is a really interesting point. Yeah, a BASO. Nice. It's like remember the meme of like the junior developer, or something, or it's like, junior developer figuring stuff out on Google, and then it's a senior developer figuring stuff out on Google, and it's exactly the same thing. Talking memes are just not great, are they? But look what I did. So I changed that, right, to a %d, which is just an integer, not an unsigned integer. And look what happened. Like, that was just a mismatch between this thing, that's an unsigned int, and I said I want to print an int. They're two different formats, but there was no error, right? This thing compiled, it just worked fine. I got the wrong value though. The compiler is not going to help you with logic errors. That's a logic error. That's not a syntax error of any sort. this might end up being a runtime error because I'm expecting it to be something and what I actually got wasn't the real value. And if I'm using that somewhere, it's going to screw me up pretty badly. So it's really important anytime we're working with basically any variable, just make sure that you understand what type that variable is and treat it appropriately. A %d is a decimal, I think. It's a, yeah, %d converts an int to decimal. Oh, programmer humor is, I as you guys know, I doom scroll Reddit every night, and programmer humor is just awesome. So fun. And it's so true. Everything in there is true. Krish asked, if %d is a decimal, why do we not get the same value as we got before? They're different. So %d is an int. That's an unsigned int. They have different ranges. And so I've got this big ass number here, and I try to shove it into something that has a smaller range, and it basically just loses its mind and says, I don't know what we're talking about here. But it doesn't complain. There's no complaint there. Like it's like, oh yeah, no, it's a -1 for sure. That's a logic error. And those are really, really hard to find sometimes. No, it's just a number. It probably overflowed a couple of times.
So if you would run this again, that might be a different number then? It might not always be
No,
-1.
it'll still be the same number because uint max is always the same.
Okay.
It's always going to be the same, yeah.
Okay, thank you.
Yeah, Aaron, it's minus. The only reason it's -1 is that, like, if you looked at the actual binary, so an int is essentially 32 bits. An unsigned int is 31, or I'm sorry, it's the other way around. An unsigned int is 32 bits wide. An int, a signed int is 31 bits wide. And so it just doesn't quite fit. And my guess is if you convert it to something else to get let's try it. Let's convert it to, I don't know, a float or something. See what happens there. And we get a 0. Like, it's just it's a format mismatch. What if the print statement, you do long, could do long time, sure. Yeah, long would give us enough bits, I think. It's kind of not the point. I mean, Rishab says, yeah, you could use long in there instead of, %i or something. I guess the point of this discussion is just understand that you do have to match the two, otherwise you get that. Like, it's not the number we expected. We really expected that number, right? All right. How about arrays? Arrays, let's go do an array. Now in this case, I'm going to use size of. So remember I said size of, oh, we didn't even use size of here, did we? Did I skip a slide? I did. Let's go use size of. Copy that. And I'm just going to comment this bit out. All right. So here the only change we make here really is that these should be indented. Wish it would indent it for me. Other IDEs do. Okay, here's a variable, right, called foo. Matthew asks, is it possible to use a plus and cast the integer to a string? Yeah, I guess. Sure, you could do that. We'll talk about casting. You'll do a lot of casts, actually. So we'll talk about that probably 2 or 3 weeks. All right, now I'm going to use this size of function. So size of is a built-in function that's part of the base language. It gives me the size of something, and size of returns returns a size t value. So the type is size t. It's just really a fancy name to say, you know what, depending on your system, it just makes sure that that type is big enough to hold the largest thing that you can store. So size T will vary depending on the system. If I'm a 32-bit machine, size T can only, think about 32-bit values. If I'm on a 64-bit machine, it wouldn't understand that. So size T is tailored to the platform. So it always returns enough information for you, depending on where you are. But we're going to use size of here. And I've got this value unsigned foo. Unsigned is an unsigned integer. So they range from minus 2 billion to plus 2 billion, 32 bits. What's the size of it is the question. Let's run this. Save it. Compile. Foo has a maximum size of 4. So I was like, 4? 4 what? In bytes. It tells me how many bytes it is, not how many bits it is or what the range is. This is how many bytes does foo take up. Unsigned is, unsigned is without the minus. So that would go from 0 to 4 billion. Thank you, Jonas. Keeping me honest. All right, so foo takes up 4 bytes on this machine. An unsigned value on another machine, like an IBM mainframe, might take up 8 bytes or 2 or 9. Like, we just don't know. And because we don't know, that's why we use things like limits, which tells us for that platform, limits.h is different for every platform. How big is it? What's my range? Size of I can use to figure out, all right, what's the size of an unsigned integer? Oh, it's 4 bytes. We're going to use that information later on when we do things like allocate memory for things. Oh, I want to store, I want to move, this value over here in memory. I need to know how big that thing is because I have to manually allocate the memory, do the move. I need to know how many bytes I need to allocate. So size of will tell me that. Here's int. Just take that one line. Get it back in there. Yes, cool. I know I'm always forgetting this stupid. What's wrong with that? Oh, yes, this. An int has a maximum size. So here, in this case, I gave it a variable, right? I said, hey, how big is foo? Here I'm giving it a built-in type, like how big is an int? Save it. Compile, run. They're the same. So an int is 4 bytes. Actually, whether it's signed or unsigned. Now I know, if I want to play with ints, I'm going to have to allocate in chunks of 4 because each int is going to take up 4 bytes. It's frightening that you don't ask questions. How about arrays? So size of works on arrays also. Let's just copy this stuff and maybe I'll make a new file for us. File, new file, save it immediately, barray, .c, paste that from the slide. And what do I need? I need that. So I'm going to use standard IO. So I need standard IO. H. All right, what's happening here? I've got foo. Foo is an array in this case. I'm setting foo's size to 6. It's going to contain 6 ints. So 6 integers in the array. And this little touch of syntax here, that's just initialization. So like often, when you're playing with arrays for the first time, you'll do a little loop. And for each element of the array, you'll stick a 0 in. This is just a nice little shortcut. It initializes all of the values in the array to 0 for me. but I want to know how big it is. How big is foo? Well, let's ask size of, because size of should be able to tell me, right? Let's save this. And now we're going to do GCC-O is, let's call it B-array. .c. We'll run it. And we get foo, the array has a size of 24 bytes. Put bytes in there just to be clear. Save it. Foo is 24 bytes. Why is it 24 bytes? Bueller?
Because we have it like we store 6 integers, and every integer is 4 bytes, so it's 4 times 6, right?
You're a genius. Yeah,
Well,
I've got 6 integers, right? How big is an int? We just saw an int's 4 bytes, so 6 times 4 is 24. It tells me how big the entire array is in memory. Just to prove it, let's make that 60. And we get 240 bytes, because now I've got 60 things that are 4 bytes each, is 240 bytes. Bernard says, when do you run out of memory? At age 72-ish, I think, is when you run out of memory. I don't know. You run out of memory when you're out of memory. Well, actually, it's only because I'm getting close to that. I got another decade to go. Thank you for the laughter. At least I know you're alive. What was the question? Oh, running out of memory. So you'll get intimately familiar with this in the course. At some point, we'll talk about processes and how much memory is mapped into a process. Bottom line is that each process, every program that's running, is allocated 4 gig of memory. So it's 32 bits of memory address space. So each process gets 32 bits worth of memory, which is 4 gig. That gets split up in a couple of ways, but every single program that's running assumes that it has 4 billion bytes, 4 gigabytes of memory. You run out when you've run out of those. And there's other issues, right? So you guys did recursion in Python and in Java, one of the two or both. And you probably saw what happens when you forget the base case in a recursion. It just keeps executing the recursion. And every time you do the recursive call, it creates a new call frame on the stack. Well, that stack is built out of that 4 gig allocation. So at some point you got a call stack, and then you recursively call, and then you get another call stack, and then another one. Eventually you'll fill up that 4 gig of space. It's 4 gig minus the size of the program, minus a couple of other things, but that's what happens. All right. Let's go back to here. So this is a common thing we do, and it's to solve this problem of not knowing what the target platform has in terms of size of types. We'll do something like this. So let me just copy all of this. Copy you, and I'll stick it down here for the moment. Yeah. Watch what it does to fix it. It says, oh yeah, it's fixed now. No, it's not. So we don't need main, right? I'm going to take this define and put it up at the top. And I need to, what else? Get rid of that and close that up. Sweet. And let's just comment this one out. We're not going to use it. All right. I've got max foo count defined. Remember in limits.h, we saw all those define statements. Really, it's just like, it's almost like defining a macro or just defining some value that we're going to use. Like, for example, if I wanted to use pi in my calculations, I do it this way. Define pi is 3.14415. I don't remember what it is. 7926, whatever it is. And then I could do things like this. Just do like printf I as value, the local value, percent, what is it, a float? Like that. Semicolon. So one of the passes that the compiler does when it's crunching down your code, one of the very first things it does is to look for these things. And then it literally just takes that number and sticks it here and then completes the compilation. Yeah, Sergey, it's actually not the same as assigning a value. It's not the same as doing this. Float pi equals, etc. That's not the same because I shall complain about that, right? Do it lowercase. It's not the same. This actually allocates memory for a variable called pi, and it's a float, so it's going to set aside, what, 4 bytes for that? This does not set aside any memory. So that's just, it's going to take that value and stick it in later. And then it'll, if you happen to need to store that somewhere, then it'll allocate the memory for it. So if we did this like that, now I'm allocating memory for a float, and I'm going to stick a 3.14157926 in it. Make sense? Yeah, cool. Yeah, Jonas had it too. So Krish, got that? It's not really a variable. When I do defines like that, it's just a value that I'm going to use later on, pre-compile basically. It's going to fill in all those for me and then do the compile. Rent. That's a weird one. All right, so let's see what happens here. We're still in B size, yeah. Oh, what did I do? There's an error. Actually, no, that's not the error, Nicholas. If you forget, it's one of the very few things that C does for you. It just sticks a return 0 in there for you. So that's not it. It's this, conflicting types. I got 2 foos. Happens when you get older. Here's one of them. I said foo's an int array. And then here I said, I basically tried to redefine it. That's a redefinition error. So that's a no-no. You can't redefine something like that. Let's comment that puppy out. Yeah, she runs. What are we looking at? We're using size of here. Oh, we're going to print pi too, but we're using the size of command or function to figure out what the size of an int is. So here's the process. I don't know how big an int is. So I'm going to use size of int to figure out how big an integer is on this box. And then I'm going to multiply that times max foo count, which is 6. And here, when I set up the array, I said it's going to be a max foo count size array. So now that calculation, the size of an int is 4, max foo count is 6, so I should get a 24 out of this, right? Pi has a local value, and foo, the array has a size of 24, which is what we expected. Let's make that prettier. Like, why would I need to do that? It might be the case that I don't have this code. Like, that might come from a library somewhere. And it's often the case that we don't have the source code for that. Like, all we were given was just some library. It'll end up being an object form, which we'll talk about soon. But like, maybe I just can't see what the source code is. Like, what is it doing? I don't know. But what the library documentation says is, oh yeah, define max foo count as the maximum size of your array, and then all of this just works. Like here, if I change this to a 40 or something, I'll get a different value, right? Now I get 160, which is 40 times 8, 40 times 4 rather. So I might not have visibility to the source, but as long as I can do something like that, then that would work. I don't know if that made sense. It'll make sense when we talk about linking later on next week. So that gives me an integer. How many do I have? Multiply them together and blah. I get 24, 160. By the way, that's a really common thing to do. Like that's really common. That line of code, you'll do stuff like that a lot. Mainly when we do memory allocations, because you need to know the size of everything. All right. So let's say that we don't even know what type is in the array. Like we're really clueless, no idea. Like all I know is it's an array of something. It's got some maximum size. Like how big is it going to be in memory? Well, I could use another built-in function called type of. That's this one. Copy that line. Just paste it over here. I know you hate that little thing. What can I do for you? It's similar, right? Let me comment out this Python. It's similar in that, can I fold here? Sort of. Actually, I could probably fold it this way, right? Not fold, great. So it's similar to what we did before. Here's what we did before, but in this case, we knew that there were ints in the array. Next, we're going to say, I don't even know what's in the array. Let's go find out what it is. That's this. What's the type of the thing that's sitting in the 0th element of the array foo? So remember array notation, 0 is the first thing, 1 is the second thing, 3 is the third thing, or 4, 0, 1, 2, 2 is the third thing. But that foo 0 is going to be the first item in the array. Don't we know the type from int foo? Maybe you don't have that. Like maybe this was defined somewhere else and you don't have access to that. But I have access, I actually have access to foo itself, but not the definition of it, which would be in the source code. So I might not know what's in there. I can find out though this way. Type of the thing in the first element will tell me what the entire array is. And the reason is that unlike some languages, in C, an array can only hold one type. So if I say it's an integer array and I try to put a float in there, in fact, let's try it. Let's just do this. Foo 0 equals 1.234. So I'm trying to put a float in there into an integer array. Let's see what happens. Nice. Let's see what's in there. So instead of printing that, let's print out what's in foo 0. Foo 0 is, or just equals maybe. Well, it's supposed to be an integer, right? So %i for an int. And we do foo 0. Let's see what happens. I did forget a semicolon. Always. So foo 0 equals 1. See what happened? It truncated it. Let's just make sure. Let's make that a double. Let's make it a float. And stick a back count on it. So now I'm just saying, all right, so I know I put a float in there. Let's see if it'll print out a float for me. Nope. But again, it compiled, right? That compiled just fine. Let me see if let me turn warnings on and see if that gives me a warning. The -W flag, big W, is for warnings. And I'm just saying I want all the warnings. I want all the candy. So then at least it warns me about it. It says, oh yeah, it looks like it should be, you screwed that up, is what it's saying. But unless we have warnings turned on, we won't see it. So here's where we didn't have it turned on. Compiled fine. That's a logic error. And again, those are really tough to find when you're debugging. Why is it 0 instead of 1? You know, Aaron, it has to do with like how things are represented in memory. So that float is going to be 8 bytes. How big is a float? Anyone know how big a float is? Yes, he has attitude. Let's find out how big it is. Printf floats are. We could look in limits too, but let's just print it. Floats are. It's an unsigned coming out of size of bytes. And what we want is size of a float. Let's see what she prints. Let's stick a back end in there. It doesn't even do a new line for you. You got to do that manually too, right? So floats are 4 bytes. But so a float has a different representation though, right? Because I have to have, what is it? I'm not a math guy. It's the mantissa and what's the other thing besides the mantissa? Sounds like a disease. I thought it was 8 too. Doubles. Try double. Doubles are 8. So float's 4 bytes, a double is 8. Right. See, we don't even know what they are. Like I thought it was 8 also. It's like, oh no, I guess it's not. You can't make assumptions about what the size the things are. You have to ask the system, what size are you? And it'll tell you using size of and type of. And back to Aaron's question about why is that 0 instead of 1 or whatever, it just has to do with the way that we represent floating point values with a decimal. Like we have to figure out that decimal somehow, right? So I think they're stored in kind of it's almost like a scientific notation, I think is how they're stored. So it's like something dot something times something, to the whatever power. We'll look at it in detail soon. We have to. I just can't remember what it is. But like, it's like we said it was one thing, we gave it another thing. They just don't match. Yeah. Foo Zero, Rayon says on Foo Zero. Oh, this one. Yeah, that's what we are just talking about. It printed this. It printed 0.0000, even though we stuck a 1.234 in there. It's because, the array itself is of integers and integers are stored a certain way. We gave it this thing. It's like, it just did its best. But again, it's not a compile error. It might be a warning, but there's no error there. Yeah, I think you guys are getting it. Like we have to do a lot of stuff by hand in C that you don't normally do in other languages. They hide all that complexity from you. All right, where were we? What were we talking about? Oh, type of. It was this thing. So this line of code, this one. So we want to know what's the type of the thing. I need to get rid of that too. What's the type of the thing in foo0? Well, we said they're integers, so it's probably going to be an int, right? And then we need to know how many things are there. There's that many, because we set this array up with max foo count. So I have that many things total. And by the way, when I do this, it sets aside memory for all of that. So I've got that many things, and they're of type, whatever is in that first element. I multiply the two things together. It's the same as doing this, except I'm not assuming the type of the array. I'm just going to go ask and see what the type of the array is. So let's clear that. And we're here. So we get the same number, right? we assumed an integer there. That came from this line, that line. And here, that one, that came from this line. So when we asked what the type was. Cool. Oh, we did that already. C's a wacky language, man. Yeah, one more, just a little trick, and this only works with arrays because of the way they're stored. It turns out that the foo here, I'll just write it. The value of foo, just foo, no brackets or anything, is really the address in memory of the first element. So it's really that foo, it points to the first element in the array. And if you think about it, you can start to like puzzle out, like, how is C treating these in memory? So if foo is it just holds the address of that first array element. So I know the address of the first guy. I know what they are. They're all ints, right? They're all the same size. So if I just say that foo is essentially the 0 value, to get to the 1 value in memory, I just add the size of the type. These are ints. They're 4 bytes on this machine. So I start at foo, I go 4 bytes in, and now I'm at the second item in the array. Go another 4 bytes, I'm at the third item, and so on. That's why C, one reason why C needs to know types. It uses the type information to manipulate this stuff in memory. If we tell it it's a float, but it's really an int, or we tell it's a double and it's really an int, the size is going to be wrong and it's going to miss, right? It's not going to fit the way it really is shaped in memory. All right, cool. Oh, so the trick is just this. We can do this. And don't be too concerned about the syntax here. We'll cover this in depth next week. Pretty sure next week we start talking about pointers and so on. And, yeah. So what I did here was I copied the wrong thing. Oh no, I just didn't copy it for me. Did it? Type of, yeah, type of. That's what I wanted. All right, same idea. But the trick is, so this little star operator, that one, just above my cursor, yeah, it's a pointer. Well, it's actually not a pointer. So that star is in that position is the value at. So in this case, star is the value at. If it's on the other side, it's a pointer. And so if you read it, it's like, all right, so foo has a size of the type of the thing, which is the value at that first guy. So the value there is going to be the same as foo 0. And again, we'll talk about this ad nauseum next week or so. So don't feel like you need to remember this or anything. But if we run it, you'll see it gets the same thing. We'll end up doing, yeah, that's exactly what it is, Matthew. That's a dereference of that pointer. It's technically a dereference operator. I call it the value at, because that's what it means. And we'll go over pointers out the wazoo coming up soon. So why do we care? It's this notion that we have to do everything manually. You can't basically won't even do it for you. Like, you have to do all the memory management. End of story. And to do that, we need to know information about what size things are in memory. And so we use type of, size of, that sort of thing to figure those out. The classic example is an array. So an array in C, like this one, that one, Arrays in C are immutable. Immutable means you can't change them, can't change their size in this case. C is the dear stuff of languages, yeah. Jonas, we'll have to find that meme that's building an airplane in different languages. That's a great meme. I don't have time to reach out to you. Are there vectors in C? There can be, yeah. But like not natively, like we have to define them. They're probably going to come from a math library for you, and then you can use them. But it's just, I mean, a vector is just a representation of some data in memory, right? And ways to manipulate it. It's not a native type at all. Arrays. Arrays are immutable. And so if I need to extend this array, let's say max foo count isn't big enough, I need it +1. So I just basically want to extend that array by 1. I can't. Other languages are like, yeah, whatever, I'll do that for you. No, in C, the way you add an extra element, like here it's 40, right? So that's a 40 element array. If I want a 41 element array, like I made mistakes, like, oh, shoot, I got to extend this array. You get the original array, figure out how big it is, allocate memory for an array that's 1 larger, copy all of the items in the old array to the new location in memory, and then delete the old array. And then reassign the variable to the new location in memory. That's how we extend an array in C. Yeah, that's it. Matthew's got it. You got to copy the array. Actually, you'll do that in an assignment at some point. So that's why we have, that's why we care about this stuff. Or certain variables local in C. Yeah, we'll talk scope at some point too. So if you just like, the rule of thumb, variables are scoped to a block. And the block is defined by the curly braces. So that's 1 block. So all the variables in here are local to that block. Pretty similar to Java. Yeah, Jonas. Although we can do, does Java, I used to program in Java and I think deliberately forgot all of it because it was such a pain to do a ton of Java. Does Java have an extern keyword for an external variable that has different scope? I don't remember. Yeah, in C we can identify something. We say we could do it this way. We'll get to this much later, but you can say extern. Extern means that variable is defined somewhere else and it's going to be pulled in on a define, or it lives in some other object file. But that is for another day, for sure. That's why we care. I got one more thing and I got 10 minutes to do it. So all these stupid type conversion things, these conversion operators in printf, it's because when printf prints something, you give it a variable name to print. Oh, if it's an I or a D, it's going to print 4 bytes from that location in memory. If you say it's a U, it's going to print 4 bytes. If you say it's a double, it's going to print 8 bytes from there, right? So you're telling printf how many bytes to output from the start of that spot in memory. And the same with scanf, which is the flip side of printf. By the way, do we go to quarter past or half past? When do we start? Oh, we go to 3:15, right? Yeah, that sucks. That sucks. All right, so scanf. Scanf has the same idea. Scanf, I'm going to read stuff in from the console. So let's look at that. Same idea. I'm going to now read a value from the console and store it in a variable. Let's grab all that. I'll make a new file called scans. Save it as scans.c. All right, let's talk about what's going on here. I've got 3 integers, foo, bar, and baz. So I'm just defining 3 integers. Now I'm going to initialize them. So foo is the same as bar, is the same as baz, and they all have the value 42. So I'm just initializing all of these to the value 42. So now I've got these 3 integer variables. I'm going to read values into them. And hey, did you guys see that there's an article where somebody figured out that some like cosmic constant really is 42. And it's like, it's that constant that separates the universes. It's crazy. I'll have to find the paper. Or maybe, who knows, maybe it was the Onion. Like, at some point it's just like, it's all the same, right? If I can remember to find it, I will. Oh, hang on, 42 paper. I'll see if I can find it for you. It was on Slashdot, I think. All right, so 3 integers. I set them all to 42. And here's scanf instead of printf. Scan just scans the console for values. The F is formatted. And so I'm looking for 3 ints, right? Int, and I'm going to put them in foo, bar, and baz. And then I'm just going to print out foo, bar, and baz. Just a regular printf statement that we're used to. That little ampersand, again, we'll go over ampersands and stars and all of that coming up soon, but it's just an address operator. So you can read that as scan these values and put them in the address of foo, the address of bar, the address of baz. So this sets up the actual memory allocation for it, right? I've got 3 integers in memory. I stick a 42 into them, but now I'm going to put values into those guys, and I'm going to put them at those memory addresses, the address for foo, the address for bar, the address for baz. And you can assume that I have to tell it the type, because that's going to be like how big a chunk it sticks into the address of foo, address of bar, address of baz. That's why these are all i's, because these are all ints. Save it, run it. Out scans, it's going to be scans.c. Blah. I forgot. Scanf is in include standard IO.h. You would think it would know. Like, why doesn't it just do it for you, right? It's like it knows what header file that's in. Like, just freaking put it in for me, stupid piece of compiler. All right, save it. Okay, clear it. Here we go. And now let's run scans. Nothing happens. It's waiting. It's waiting for me to type in 3 values. 3, 4, 5. And then I print them out. Foo is 3, bar is 4, baz is 5. Cool, huh? Watch this. 3, 4, 5. Oh, that didn't work. I got those default 42s in bar and baz. Anyone know why? Bueller? No comma. You guys are awesome. Yeah, so here's this is the format string. This is what scanf is expecting. 3 integers separated by commas. And when I didn't put the comma in, it found the first one fine. And then look for a comma. It's like, I don't see any comma here. You hit the end of the string. It's like, oh, I only saw 1 value, and so I only set 1 value. So you got to put the commas in. If I wanted spaces, I would do it this way. Just put a space in. Space, space, space. Save it, run it. Oops. Pilot before I run it. And now 3 space 4 space 5, that works because I said in my format string, they're going to be separated by spaces this time. And normally you'd print something else like please enter a couple of numbers separated by spaces or something, just to give the user a little hint. Otherwise you got to like just try it and oh, it doesn't work. So that's scanf. How does it know the space is not an int? It doesn't. It's only looking for, oh, I'm sorry. A space is not it's not a numeric value in ASCII. So space is the ASCII value 20, and numbers start with something else. Yeah, scanf, very similar to CN, but we do the modifiers here instead of in the stream in CN. So pretty close. Same idea, I'm just reading stuff from the console, right? All right, so that talks about that. We just did that. That ampersand, as I mentioned, is just the address. You're going to get tired of playing with addresses at some point. Oh yeah, let's do this one. This one's cool. Copy that and let's put it over here. I know. So what's happening here? Here I'm saying I want the address of foo. So I've got foo here, right? And the address of bar and the address of baz. That's what I'm printing here. Remember that ampersand's the address of operator? So print out the address of foo, the address of bar, the address of baz, and I'm going to print them as %x's. %x is a hexadecimal value. Save it. Compile it, run it. 3, 4, 5. And now here are the addresses. Those are the memory addresses that have those ints in them. They're each 4 bytes, right? So this one starts at B8, C4, 90, 34. The next one is 4 bytes from there. So that one ends in 34. This one is 38. 38 plus 4. 8 plus 4 is 12, which is a C. So the next one's at 3C. So they're 4 bytes apart in memory. Cool, huh? I love this stuff. So what's the distance? It's the size of int. There's a couple of quirks of scanf. We'll run into those probably at some point. And so when we're really doing like serious like inputs and such, we'll probably use readline instead. It's just a similar thing. It just has a little more bells and whistles, I think. But you'll see that at some point soon. Oh yeah, Rashad. Yeah, for that, yeah, CN takes inputs, and actually, it goes deeper than that, really. So they both work on streams. So this is an input stream on the terminal console I/O, right? And CN does the same. CN takes a stream as an argument. All right, guys, it's 3:15. So on Thursday, we'll cover the rest of the stuff that I thought I was going to cover today. Basically, we're going to take a look at conditional statements. They're pretty similar to what you've seen before. And we'll look at 3 kinds of loops. Shouldn't be too much of a pain. And then actually, once we've seen that, I can release your next assignment. So that's all I have for you today. I will see you all on Thursday. Peace out. Take care, guys.
Thank you.
Thank you, Professor.
Thank
See
you.
y'all later. And just shut off recording here. Stop that.